Great. Well, today's example, as I mentioned, is going to be on some simulated microarray data. I believe I sent around several attachments. The ones that you will have are this gene express file. If I just open that up, you can see that there are, this is a direct, we've used the read table function a lot. This one was created by write table. So the write table function has created this, this table of data that we're going to work with. Later on in the hour, we're going to talk, in the second hour anyway, we're going to talk about how we simulated this data set to work with. Oh, I should mention, if you have not received the files, I do have a thumb drive. Ah, perfect, Maria is here, great. Sit. Okay, grand. So these data, the sim gene express set, is what we're going to use as our test data. And then we've got this diff expression file as well that we're going to work with. So I'm going to create a new folder for this in my documents folder using the new folder option. And how about we call this gene express? So it's a gene expression exercise. All right, so we open that directory. We see that it's empty. Now we're going to add these two files to it. Now mine looks very slightly different than yours because I've added some code this morning, but we're going to just let that be how it is. So I'm going to copy diff expression and sim gene express into this directory, which is located in documents, gene express. All right, if you're doing this on a Mac, you're going to have different locations for some of these things, but you can create whatever directory in whatever place you want for it. That's all going to be fine. So if we are to look at the gene expression data here, and we just click on it, we see that line 1 has a bunch of headers, line 2 has this, and so on. I'm going to actually open a copy of this in Excel just so we can visualize it a little more easily. So I'll pop open Excel. The difference here is that I want all the columns to line up properly. So I'm going to open up a blank workbook for a moment, and then hopefully, just by dragging sim gene express to that, I'll have something decent. Oh, it didn't open right. The reason here is that it's not parsing correctly. The values that have been written in here by R are separated by spaces, and it didn't recognize that as a legitimate way to separate the values. So I need to close that file and reopen it. And this time it can ask me how it should be split up. So we specify that the first line should be regarded as headers. My data has headers, and it's delimited. So if you've written a file, you might have used the first 12 characters for the first column, and then the second the next block of 5 characters for the next. If you've got something like that, then you have a fixed width column table. Instead, we have delimited values. Frequently, you'll see tab separated values or comma separated values. In this case, it used white space, so we have to correct that. So I'm going to just click space here, and you see when I click space, these columns down at the bottom separated out correctly. So I'm going to just say finish with that. There's another kind of oddity when you've written a table within R. You frequently find, having opened it in Excel, that your column headers at the top are offset by one position. So I'm going to cut them from here and paste them here. All right, all of that was just to give us a chance to look at this table in a tabular format. So we see that we have a first, well, the first column is just an index. What item number is this in the series? The second column is labeled gene. So we needed to have some sort of label to attach to each of these expression values. Normally those would be gene names like SARC or RAS or whatever. I mean, just the set of gene names that we're accustomed to from human gene names. But in this case, I decided to go with randomized gene names. So each of these is 5 characters long, and they're just random series of letters. So, quick question. If I have gene names that are 1 character long, how many different possible gene names are there? One letter long, I should say. If I have gene names that are just 1 letter long, how many possible gene names are available? Someone want to venture a guess on that one? How many letters are there in the alphabet? 26, right, okay, great. So we've got our answer. So if I don't take caps into account, I have 26 possible letters that I can use here. Now, I have used 5 letters here. So how many possible gene labels do I have in that space? 26 what? To the power of 5, that's right. Right, so 26 to the power of 5 is actually quite large. However, you can imagine data sets in which a great number of transcripts are measured. How many transcripts are there for the human transcriptome? I think current estimates are like somewhere between 70 and 100,000. So with something like that, you really do need to have a fair number of gene names to avoid collisions here. I started actually with 4 letters in each gene name. And what I found was that when I simulated 1,000 gene names of length 4, I occasionally ran into collisions. So I decided to go with 5 to avoid that. So, all right, that's neither here nor there. But this is the sort of math puzzle you should probably have in the back of your mind. Comes part and parcel with bioinformatics. All right, now I've included red 1, 2, 3, 4, and 5, columns C through G. And I've got yellow 1, 2, 3, 4, and 5 in the next 5 columns. So in each case, the data for each gene is simulated, and we've got 5 values. Think of this as 5 replicates in each of 2 cohorts. So this is one of the simpler kinds of models for us to work with. Data that are continuously distributed, 5 replicates each, and so on. So if you were just to glance at this, do you immediately see a gene that you would call differential? Any of those pop out for you? Let's use the numbers from column A as their identifiers. So is there one there that looks like a difference to you? We're going to be asking the computer to do this, so it's good if we have our own intuition about it. Number 14, is that row 14 or is that number 14? Number 14, so SYLBC. All right, so as we look at this, we've got 4.09, 4.18, 4.92, 5.0, 4.6, and on the right we have 4.86, 4.97, 4.44, 3.55, 4.22. You feel good about that one being a difference? Okay, I happen to know it's not actually in this case, but one of the reasons why these differences appear is that there's some random variation. So I want you to think about the fact that for some subset of these genes, we have actually different means between the 2. But that difference in means is added to by an additive error factor. All right, so we have some difference that's real, and then we have variation around that difference. Now, I'll just give you a clue about what I'm doing with this data set by pointing out that I've made 1 in 10 of these 1,000 genes actually differential. They have a real difference in their means. Any other differences that we see in means are just artifactual. Okay? So as we proceed, you should be able to think about, okay, well, what's the mean value for red, and what's the mean value for yellow, and correspondingly, how much variation is there around the mean within red and within yellow? Okay? Because your ability to find a real difference in these data sets requires that you have a good mean difference and a small enough variation around that mean that you can actually tell them apart. Okay? So that's kind of a very basic primer to difference testing. As we get into the biostatistics module for our division, you'll have much more on that topic than you care to. But for now, I want you to always remember that if you're trying to find a difference in a biological data set, the variation must be small enough that the difference between means is detectable. Okay, enough of that. Let's actually get on to our test here. So onto our examination. Now we have some code that we want to deal with here, but first off, we need to check that everyone has Ggplot 2 installed. Now, if you are connected to the network right now, you're in good shape. If you're not, you're going to run into problems when we do the Ggplot 2 part. So I'll just point out that you can install a package direct from the command line here. So I would say install packages. You can see that as soon as I start typing install, it gave me this function. That's great. And now I'm going to give it a name, Ggplot2. Is that font visible? Not very. So let's try boosting our size. Zoom in. Okay, I'm going to blow this out to full size if I can. Oh, that's not the one. That's the one. It's just not going to be bigger than that. Okay, can people read install packages Ggplot2 there? It's a marginal case. Okay, I'm not sure how to make that any bigger on this screen. Now you'll note that when I run that, the software freaks out, and that's because my computer is not connected to the network right now. Normally, it would go through the process of installing all the supporting elements. So what we want is a command that looks like that. Oh, crap fire. Well, I'm going to just roll it up myself. Oh, well, it's not going to roll up. I could just pull that monitor out of the way, I guess, but there we have it. So there are also menus you can use for manually installing this, but since that's something that may take some network time, I wanted to let you know about that right up at the front. Install packages Ggplot2. You might be asking, what is this Ggplot2? And I'd have to say, Ggplot2 is one of the most phenomenally successful packages in R. Lots and lots of people use Ggplot2 as their essential library for plotting these data. So Ggplot2 is your friend. Okay, now I am going to move into the folder we created, this gene expression folder right here. I need to specify that this is the directory where R is looking as its current working directory. So I'm sitting inside gene expression. I go to the More menu, and I say Set as Working Directory. And I can double check that I'm in the right place by running list files. And you can see that both of those files show up. Okay, is everyone... I'm sorry, I can boost that up. Right, so I've set my working directory to Gene Express. I've run list files, which is the same as like a directory command, essentially. That gives me back these two files. Now, I would like to look at this script I've created, this differential expression text file. So I'm just going to click on that, and you can see I have a whole bunch of stuff in here. I've got a generate strings of random. I'm going to make this a little larger for just a moment. This is the software we're going to be running today, the whole set of commands. Up here, I have a bunch of code that's really devoted to creating random gene names. That's right here. Simulating our gene expression data. That's right here. Oops. And then down here at the bottom, I finally get to the code that we're going to focus on first. So if you scroll down to line 44 of that, you can see read the table into memory. To open this, I just double-clicked on that first, or clicked on the file name itself. Okay, and that should give us this section about line 44. So how does, I see puzzlement, so I'm going to stop right here. Yes, question?
I'm sorry, I have no idea what's going on.
Oh.
I can't get my thing to work, so I don't know.
Okay, has RStudio started successfully for you?
Yeah, but it looks different to yours.
Okay. Are you running on a different operating system? Okay. You're running Windows, that's good. Oh, you've opened R, okay. So you're running R rather than RStudio.
Oh, is that, okay.
It's okay. I mean, that's actually where I work most usually. Okay, so I can do this in both. I'm sorry, I should have explained this. So this is the RStudio interface that helps you keep the files you currently have, the variables that are currently in memory, and the code all kind of side by side. You're running R itself, which is how I normally do things, actually. So this is what R looks like by itself. It's a little less friendly, as you can see. So if I wanted to look at this code, I would probably open it in my favorite text editor, just drag that over there, and boom, now I'm looking at it in Emacs where I can just type to my heart's content. That's how I normally use R. But you are using it in the command prompt mode instead of with RStudio wrapped around it. So in this case, you'll need to set your working directory a little differently. You remember when I told it in RStudio that I wanted it to, when I was in RStudio and I wanted it to set my directory, I came over here to the More menu, etc. it created this command, set working directory to your home directory GeneXpress. But I'm not sure where on your laptop you've copied the files. Was it on your desktop? Was it in Documents?
My download folder.
Your download folder, okay. So I think we can do this. Let me, so if I use set working directory in standard R, I'm going to have to give it my directory that's going to be, I hope this is right. I could be wrong. Nope, that's not it. Can I just change to that? Yep. Okay. I think the best way to do that would probably be just to set the path explicitly. So if I have my files sitting here, if I click in Explorer and I click on the address bar, it gives me the explicit path to that directory. So mine is C users dtab documents GeneXpress. So yours will probably be C users your username desktop GeneXpress. That can be a little hard, sorry. Yes, it is easier to change your directory this way, but for now, might I suggest that you move your file, move the GeneXpress directory into Documents. It will make it easier to jump to. Okay. So if you are sitting in, if you create a folder inside here called GeneXpress, I'm going to just copy the directory to that. Well, it is in that location. Okay. So mine is sitting in the GeneXpress folder of documents. So I'm going to say set working directory GeneXpress, just like that. Okay. And now when I do list files, I see both of those. Okay.
I'm sorry.
It's okay.
It's not happening for me.
Okay. Well.
How do we get to RStudio?
Okay, RStudio, you download it and install it.
Oh, okay. So
yeah, it's a separate program from R altogether. It includes R when you download it.
okay.
It's a little strange. Sorry. Okay, so the easiest thing to do if you're going to follow along in R is to move it to your Documents folder, to have your GeneXpress folder in there, and then you can change to it using that command. Tilde means your Documents folder / GeneXpress.
It's in my Documents folder now, but I don't get the address thing at the top.
Okay, let's ignore that. Is the folder is called GeneXpress?
Yeah.
Okay.
I'm sorry. Maybe I can just come afterwards. I don't want to keep up the class, but
I understand. If you can install RStudio, the demo would be a little easier to follow. But yes, you can do everything in R that you can do in RStudio. It's just not as friendly. Okay, that's fine. That's fine. Great. Okay. So, any other questions before we move ahead? All right. Now, I'm going to move this bar over to the right because I have rather little screen to work with here. You have your full width of screen. So I'm going to put this text, the text file, the differential expression text file at the top, and have my console down at the bottom. Oh my goodness, this is just vexing me. Okay. So the way that these workflows tend to go in R is that we read a file that's got all of the data from the flow cytometer or from the gene expression microarray stuff or from the proteomics software, whatever. We're going to read a file, we're going to perform some sort of math on it, and we're going to visualize it. So this software contains all three of those functions within it. The other thing is that the way that I've written this code is I've tried to follow the way you should do it in R, rather than the way that I tend to do it. Now, I'll try to explain how those differ from each other as we move along. So for the first part, we're simply going to read that GeneXpress file into memory. So I'm going to grab this first line right here, and I'm going to copy it to the clipboard come down here and paste it in. And hopefully you just see no response from that. It just reads it into memory and you're done. So the command we've run is read table. I think you may remember having seen read table yesterday from some of the examples we did there when we were producing the frequency histograms when we look at box plots. So far, this is all in the email attachment that I sent around yesterday. So we're going to read table. This is the file that was created by R for us. And we have to specify that it has a header attached to it. If you don't specify that it has a header, it thinks that those row names like red 1 and yellow 1 and so on are part of the data column rather than the label for it. And you can check that that is read correctly by running a summary on the object that came from it. Okay, and I'm going to have to blow that up full screen again. All right. Yes, sir.
This is just stick with the.
Oh, yes. Okay, does anyone else need the updated files that include the Ggplot2 business? I'll include this on the email I send out later today as well. All right, so having run the read table on this input file, we got back an object that has a gene field, a red 1 field, red 2, red 3, red 4, red 5, just as it was when we looked at it in Excel. So we feel good about that. I told you that it had 1,000 rows in it, 1,000 different genes. So does that correspond with what you're seeing here? Do you have a way of seeing how many different rows there are in this table? You do have one, actually. You can see that there are 1,000 distinct gene names here because we have 1, 2, 3, 4, 5, 6, plus another 994 of them. But there are definitely nicer ways to see whether this gene expression object has everything in it that we expected. So one of the simplest there would be the dim command. When we run dim on the gene expression object, we see that we have 1,000 rows and 11 columns. And whenever you're dealing with a table in R, keep in mind that the first number is how many rows, and the second is always going to be how many columns. So we have 10 expression values plus 1 that's a header. Grand, we're in a good place so far. Now let's return to our source code to see what we're doing next. All right. Now this next line has an awful lot going on in it. And as I said, I've tried to write this the way that an R programmer would, not the way that I would. So this is a very much abbreviated version of how we would go about applying a t-test. First off, what is t-test good for? What's that? Comparing two variables, okay, and you're doing so under the null hypothesis. The null hypothesis says there's no real difference between these means. So if you see differences between the two means, is that within the expected amount of variation that we should expect, essentially? So we're going to be applying a t-test at the end of the day, but we can't do one t-test for all of the reds versus all of the yellows for all 1,000 genes. We just can't do that. That's not what t-test is designed for. Some of these genes have very, very low signal intensity, and some of these genes have very, very high signal intensity. So it doesn't make sense to compare the red values for a very low expression gene to the yellow values for a very high expression gene. That's just nonsensical. So instead, we need to be running t-tests one at a time on each gene. All right, how can I help make this any clearer?
Can we maybe put the lines off because I'm struggling to see the...
Yes, I think we can. Sure. Yes, I'd like you guys to be able to follow along. All right, now we're just in the dark. Is that all right? All right. I'm sorry, yes, it should be possible to make this a little bigger on screen, and instead it's not. So, okay. Well, now I'm looking into the projector light. That's okay. So t-test is kind of the first line of defense for people. Most of the time when people think about doing difference testing, students' t-test is one of the things that they work with. So to give away one of the best punchlines of the statistics class, I would point out that it's called student's t-test with a capital S on student, because the guy who invented it was forced to publish under a pen name. The pen name was student, because he was working for a brewery at the time. Just a little bit of a side. So we want to run a t-test, and that t-test is going to take as input 5 red expression values and 5 yellow expression values. And we're going to ask, do these data look consistent with our hypothesis that there's no difference between the means? So, in effect, we need to run 1,000 t-tests. 1,000 of them. So, one of the ways that we can do this is to loop through these genes one by one by one. So, yesterday we talked about looping. Does everyone remember that? So one of the first type of loop we talked about was a for loop. So you can imagine a counter starting at number 1 and letting us run a t-test on row 1, and then go to row 2 and run a t-test on row 2, and then go to row 3, run a t-test on that. And each time we run one of these t-tests, we could then store it to a vector. Okay, does everyone see how that's possible? All right. But in this case, we're using a function called apply. And apply makes explicit use of the fact that R is designed for parallel computation. It's got a huge number of these arrays that it's going to pull out. The one for gene 1, for gene 2, for gene 3. And apply allows you to apply that same function across all of them. Now there's a lot of mystery and confusion around apply and some of its cousins. But we'll try to walk through what it's doing here. So first off, it's working on the gene exp object, right? So that's the one we just read right off of the read table command. What kind of data structure is gene exp? We can find that out, right? I can come back to console and say type of gene exp. What is it? It's a list. We have some other options. We have the structure command. Whoa, look at all that. So it's a special kind of list. It's actually a data frame, which means that it's a whole list of vectors, each with the same length. So we're going to run this. Gene exp is what is the target of our analysis here. And in our apply, we're using a special kind of indexing on it. Everyone see that? The little square bracket, -1, n square bracket. So what does that do? What's a -1 mean? We said yesterday that if I wanted to grab out just the first column of gene expression, I might say gene exp bracket 1. But what's this -1 business? -1 is actually a special bit of syntax for indexing. So let's just try it. I'm going to start, oh, sorry, not there. I'm going to come back to my console here. So we already said that gene expression, if I just run summary on gene expression, I see that I get back information on 11 columns. Now let's try running the same thing, but this time let's add in this little subchange, this -1. Everyone see that? All right, when we run this, something happens. What vanished? The gene name itself. Okay, so this is a special version of indexing. By putting a negative symbol in front of the number 1, we strip away the first column and keep everything else. So we can use indexing to grab out a particular column, and we can also use it to subtract off individual columns, or multiple columns even. So here we have used a bit of indexing so that the only values that apply gets to see are those from columns 2 through 11 of gene expression. So only the numeric data from our data frame get passed to the apply function. Okay, so that's sneaky. The next part of this is the value 1, and if you look up in help, the instructions for apply, well, hopefully you won't be as bamboozled as I am, because I find it very difficult to understand, but nope, something didn't happen there. Come back to me. All right, here we go. So I'm going to ask it for help on apply. It's just question mark apply with the curly braces on it. And we see that there's help for us. The 1 is passed in as something called the margin argument. So apply knows that you have a whole pile of data over which you're going to be applying some function. But does that function take individual rows from your table, or does it take columns from your table? In this case, we want each gene, each row, to be treated as a separate entry. So apply is going to run t-test once for each row. By giving margin equals 1, we are compelling it. Oh, go away. All right. We are telling it that we're going to do this in a row-wise manner. So this first part strips out the gene label. The second part says deal with each row separately. And then we're going to apply a function on the remaining data. So at this, oh, yes, sir?
Before you go back, I'm struggling with getting basically quite very well. I'm still on that Unix and trying to basically get those summaries and get that stuff done. Always getting an error.
Okay. I'm going to take a quick look at what the error is. All right. Oh, it didn't correctly open. Have you set your working directory? I'll set that for you. To set the working directory, we come over to the More option on the File menu and say Set as Working Directory. Okay, and now when you read the table, it reads into memory correctly. Yeah, okay, sorry about that. Good question. I want you guys to be able to follow along on your computers if at all possible. I realize there's a lot of complexity to this. So you're hanging in there well. Keep asking questions. We will get there. Okay, other questions before we move ahead? All right. So we've already said that apply is a pretty dense kind of command. What is this business about x 1 through 5 and x 6 through 10? Does anyone get that? What are the columns in our starting data frame that we want to compare to each other?
Isn't it 3 to 1 to 5 would be 30 and 6 to 10?
Right. So we had a little change pop up between our from the original gene expression and the gene expression -1. Before, the red values were columns 2 through 6. 2 through 6. Yes, that's right. After we ripped away the gene column, though, the new first column is a red value. So this code that we've run, where did my, okay. This code that we're running is going to strip away the first column, and after it's done that and grabbed out an individual row, the first 5 columns need to get compared to the second set of 5 columns. On those, we run a t-test, just using the t-test command. It's built in, after all. And we have this $ p-value. We saw $ yesterday. Does anyone remember the context of that? When we were looking at the list data structure, I think we said H equals the histogram of something or other, and then we looked at the structure of hist. So the value that came back from hist was a list, which included things like bin sizes, bin boundaries, center points, frequencies for each bin, etc. So those were data presented in the format of a list. So when we have this structure, what we see is that t-test is also going to hand back an object of type list. And one of the values on that list is the p-value. So we can actually do a quick example of that down here. So let's. I'm going to just run a straightforward little example here. We're going to say t is equal to t-test, and I'm going to throw in some numbers here. So I want 3 numbers here. Oh, sorry. I have to do these as a set, as I recall. Oop. Comma C. Yep. Oh goodness. Oh, and I missed a closing parenthesis there. That's why it gave me a plus. Okay, so t is an object that's returned by that t-test. So if I just hit t and hit enter, I get the current value of that. And we see that it ran a Welch 2-sample t-test, which means a special kind of t-test actually, but we're not going to get into that right now. We passed it the numbers 3.7, 2.8, and 3.5. We also passed it the numbers 6.3, 7.2, and 6.3. In this case, we had a p-value of 0.001339, and there it is. So this is the pretty format for it. But if I run a summary on t, I'm going to get kind of a, sorry, it's a struct of t. No, structure of t. Okay, when I look at the structure of t, that's the object that just came back from this t-test, we see that we have a statistic, a parameter, a p-value, a confidence interval, an estimate, null values, etc. Right? So that is a list. And if we want to grab out just the p-value, we can use $p-value to grab that field in particular. So if you just hit t by itself, you get back this kind of nicely formatted thing. But if you want to grab just the p-value from it, you can say $p-value. All right? So this is the number that we want to capture as we do t-tests all up and down this gene list. Okay, so in brief, this one line of code is doing a whole pile of work for us. It's serially passing through all of those rows of gene expression values and performing 1,000 t-tests for us. So what do you think? Is that a 5-minute exercise, or is that a 30-second exercise, or is it so fast as an eye blink? Well, some of you have already run it, so that's not quite fair, but that's fine. I'm going to catch up to you now. I'm going to go ahead and run that command. And eye blink. Within less than a second, it has run 1,000 t-tests. So, oh, sorry, that was the read table. Ha, gosh. I'm going to run everything up to this. So, all right, grab that. Copy that. All right. There we go. Well, it didn't take forever, did it? All right. So one of the things that we did here was to create a new vector. So if we do a quick summary on this, Ggplot, we see that we've created a new numeric vector that's fairly long, should be, length Ggplot. We see that it's 1,000 entries long, which is what we expected given that we fed it 1,000 gene rows to deal with. So we had values from 0 up to 0.9997. Okay, and how do we score a p-value from a t-test? What's good? What's the standard lore on making sense of a t-test p-value? You want it to be low or you want it to be high? Low. All right, so generally speaking, when we run a t-test, it's because we have an itching suspicion that these sets of numbers are actually different. So we're going to ask, how probable is it that we would see a difference this big if there, just by random chance, if there were no real difference? So a low p-value is our way of rejecting that null hypothesis. So I'm going to do just a quick exploratory data plot to help us evaluate what came back. I'm going to run a plot on the sort of Ggplot. So, oh, sorry, I realize that it's not very easy to see. So the function, all right, so the one I just ran looks like this. So this is my vector of 1,000 p-values. I've sorted it from lowest to highest, I think is the default, and then I ran a plot on it. It's an easy kind of plot to do here. And when you look over here, you see this straight diagonal with a bit of a hockey stick on it, right? So what we're looking at are some extremely low p-values against a background that's uniformly distributed. We can look at that another way. We can run a histogram on Ggplot. Well, that looks pretty level, doesn't it? But then look at this. We have this blob of values down here at very low p-values. So that's good news. I know what the answer is in this data set. 1 in 10. So 100 of these 1,000 rows have real differences. And they should have very low p-values. But if I didn't have those differences in here, if all of them had the same means between red and yellow, you would expect this to be completely flat. So that's one way you can evaluate whether your statistical testing strategy is sound or not, by simulating a bunch of data and seeing if you get a nice flat p-value distribution that comes out of it. Okay, so good news so far. Everything is working more or less. I'm sorry for folks who haven't been able to follow along there. So that's just 2 lines of code. Read the table, compute a whole pile of p-values. One of the other questions that people really like to get out, especially the biologists, is not just, is this gene differential, but are these differences so great that they're biologically meaningful? And the proxy that people generally use for this question is, do these expression values change by 2-fold in either direction? So one of the things we're going to compute are log fold changes right here. Once again, we're going to compute log fold changes once for each gene. So just as we did for t-test, we're going to use the apply function, except this time we're going to sum together all of the 5 red values. We're going to sum together the 5 yellow values, compute the ratio between them, and then do the log to it, a log transformation to it. In this case, natural log, but you can do it any way you like. So if I copy that over to my console, I should see a very rapid computation go through. What did I just botch here? It didn't like that very much. It worked fine on my desktop. We're going to say it's fine for the moment. Log fold changes. Looks fine. I'm not sure what those warnings are about. Probably I had a 0 in there somewhere. What does log do when you have 0 values? It panics, gives you negative infinity values. So, not sure why it's producing that error here. We'll just call it a day. Okay, so now I have for each gene 2 different values that I've computed. One is, what is the p-value associated with the statistical significance of any difference between means? The second part is that I've computed log fold changes. Now, why did I do log? That's kind of odd, isn't it? I did log because I want to have some degree of symmetry between values that are 2-fold up and values that are 2-fold down. If I'm looking at the linear relationship between these genes, the ratio of these intensities, if I have 2-fold as much in red, I'm going to get a value of 2.0 for this. What's the value that pops out if if the yellows are twice as intense as the reds? Anyone? We already said that if the reds were twice as intense as the yellows, this evaluates to 2, and then I take the log of it. But what does it come to if the yellows are twice as big as the reds? 1/2. 1/2. So 1/2. It means that if I have some genes that are much higher in the yellows than they are in the reds, I would get values that are closer and closer to 0. But instead, I want these to spread out nice and evenly along a number line. So if I put them on the log scale, and there's no difference between the two, the log fold change is 0, because the linear ratio is 1 to 1, essentially. Okay, so this is going to force things that are big in yellow to go to negative values, and things that are big in red to go to positive values. A log fold change. That's why a lot of the data we see expressed in posters use the log scale, because they're ratio information, and ratios tend to be very unstable numbers. All right, let's return to our script. What's our next line? Ah, this is one of my favorite concepts to talk about. And you can be sure in the Biostatistics unit, my division, we're going to be talking about multiple testing correction because darn it, we have to use this. It's one of my favorite things to pester people about at their defenses, seriously. So, we are going to adjust these p-values. Okay, so there's a really famous cartoon made by a guy named Ralph Monroe in a cartoon called XKCD that explains multiple testing correction very well. I'm going to just plagiarize from that grotesquely here. So, imagine that you, a careful scientist, are going to evaluate which color of jelly bean causes cancer. Okay? We are going to use a threshold of a p-value below 0.05, which is what everyone does in statistics. So we're going to start by my eating a bunch of red jelly beans. Maybe we'll feed a whole bunch of people. Do I or do I not drop dead of cancer? I don't. But as we keep testing different colors, tan ones, white ones, oh, those little spiced guys, those are so happy. And of course, black jelly beans. Everyone has this special feeling about black jelly beans. Personally, I love them. So I'm doubling down on that experimental trial. We go through all of these, and each time we test another color, we have some chance that randomly, we're going to find a statistical difference. So, if I try 20 different jelly beans, 20 different colors of jelly beans in this trial, the chances are that one of them will prove to have a p-value of less than 0.05, even though that jelly bean does not cause cancer. Okay, so we're going to adjust these p-values using a method called false discovery rate, or the Benjamini-Hochberg method. In the case of R, that's a one-liner. If you want to do this in Excel, you're going to have a little bit more time required. So I'm going to copy this one command, and I'm going to apply it right here in our other window. Okay, very quick. So what the structure for this function, by the way, is pretty straightforward. We're using the p-adjust function. It's built into R, very standard toolkit. We're going to apply it on the p-values that came back from that series of t-tests. So what's the structure of GE p-values? Is it a list? Not so much. It's actually, this is just a vector. It's a vector of 1,000 p-values. And we're going to apply a method named FDR that's built into the p-adjust function. And out pops GE adjusted p-values. So if I look at my vector that I started with, p-vals, I see it has 1,000 entries. Here I have adjusted those p-values. Again, it's 1,000. So are these numbers actually, has it done anything to those numbers? Let's run the summary on GE p-vals. Let's run the summary on GE adjusted p-vals. Did they change? Well, how about the middle of the list? If we sort all of those p-values, did the middle change? You can find that, from the median. So the median for the p-values before we did any adjustment was 0.465. After we did it, it jumped. Look at that, a huge jump from 0.917. So that's tremendous. So this adjustment process has greatly reduced our chance of calling an individual test significant when it's not, a significant disruption from our null hypothesis. Okay, so now we started by reading our file. We've applied t-test across it to get p-values. We've applied log fold changes in order to find how much the difference was. We've now adjusted the p-values. Finally, we've made it to the place where we can start plotting. So this first example that I've provided in this file is using base graphics, which is to say the plotting functions that are built into R itself. So I'm going to start by running this first line, and we can evaluate what results from it. Figure margin's too large. That's because I don't have it I haven't given it enough room. I'm going to rerun that command. Ah, much better. All right. What we have is called a volcano plot. I'm sorry, it's over on this side. So we have log fold changes on this axis. So what do we get when red and yellow are the same level on a log fold change? Standing O, it's a big 0. So we have a 0 difference between the red and yellow. When the ratio is 1, we fall right here on this midline. So these are up in red, and these are up in yellow. On this axis, we're using the negative value. We've subtracted the logarithm of the p-value. That probably sounds completely arcane to you. But the thing that I want to tell you here is that the closer a p-value is to 0, the more we care about it. And one of the ways to emphasize that really strongly is to plot them on a negative logarithm plot. You see this all over the place. In all kinds of bioinformatics, in all kinds of biostatistics, we find a negative logarithm is an easy way to transform p-values to highlight the ones we actually care about. So in a negative logarithm, we see that values like this one are extraordinarily close to 0. Values like this one, very close to 0. But once you get down here, these are p-values that no one would ever write home to mom about. Okay, so that's the plot that we've now generated. I wanted to make some corrections to this. Oh, so this is called a volcano plot. Does anyone know why it's called a volcano plot? Imagine that I'm a mountain right here, right? I'm losing my top, right? So we have this spray of p-values and fold changes spilling out of the top. So this is one of the most common ways to visualize differential expression data. Is it limited to microarrays? It is not. People use it in proteomics, people use it in flow cytometry, people use it in all kinds of different fields. So anytime you have fold changes, well, log fold changes, and negative log p-values, and you visualize it, you can call that a volcano plot. It's a very handy way to organize an awful lot of data. There are some limitations to this plot, though, and there are some things that we want to do to fix it up, to make it a little easier to read. So when your professor comes by your slides, he or she can say, oh, I see the stuff I should be paying attention to. So let's return to our source document. There are a couple more lines we want to grab. I'm going to shove this off to the side again. All right. So first off, we want to ignore any p-values that are too high, that fall outside of negative log of 0.05. So I'm going to use the abline command in order to add a line across here. Because right now it's not obvious where 0.05 is. Right? We're doing this in the negative log scale, so who knows what the negative log of 0.05 is. So we're going to grab that command, pop over to console, and paste it in there. Okay. And I'm going to open that wide out again. So having made this change, we've now thrown a line across here, and this now represents an adjusted negative log p-value of 0.05. 0.05 is down here. This is the negative log of 0.05. So anything below this line, we can say did not produce a significant p-value in our t-test. So these values up here are the ones that we care about. But the biologists in the room say, my goodness, the red versus yellow ratio is just not very impressive on many of these. I mean, stuff like this, so close to 0. Do we care if it's statistically significant, if there's a 5% more of this protein in reds than in yellows? Not so much. So we're going to help our figure a little bit more by adding 2 more lines. And they were right in there. Feed the table into memory. Here we go. So now we're going to add 2 new AB lines. Console. Okay. I've added 2 more lines. The first one that I added specified that it was horizontal, that's what the H means, and it was going to be at negative log 0.05. The next 2 lines that we're going to throw in carry 2 different ratios into consideration. One is that we care about things that have a log fold change of more than 2 to 1. And we also care about things that have a lesser log fold change than 1 to 2. So we have to consider both possibilities here. So in effect, our volcano plot has now been split into 6 regions. This stuff in the middle right here, nobody cares about this. These are not significant p-values, and they do not represent major fold changes. This box over here, people don't care about it because they don't have significant p-values, even if they are heavily slanted towards yellow. And in any case, there were no points in that space anyway. Over here, we had the possibility of genes that were heavily overexpressed in red, but had non-significant p-values. Again, empty. This stuff in the middle might seem tempting to be interested in. It's got a nice low p-value. It made it into this space, but it doesn't fall in it. It's less than a 2-to-1 ratio red to yellow or yellow to red. So again, this stuff we don't care about. That leads us to this area and this area. Yes on the significant p-value, and yes as a big enough fold change for us to care about. All right, so that's a straightforward look at how to do a volcano plot using this, using R. I'm going to put this image away for just a moment because it's otherwise going to fuss at me. I'm going to take that one away as well. How many of these do I need to nuke before I get back to nothing? I made a lot of plots today. Okay, let's drag this back over. So I think already most of the people here would say we did a lot of work, right? I mean, that would you say that would take you a good afternoon of work to sit down and get all the code just right? I'm asking to feel better because I spent all afternoon trying to get the code just right for this. This is not how I would normally code this because I do for loops, right? I would write a for loop that runs from gene to gene, and for each one it would compute a p-value. For each one it would compute a fold change, and so on. Using the apply function is a whole lot more compact, but it's not something I understand very well. So we can see that all of that code, including comments, stretches only 15 lines of code. So you can do an awful lot of work in a very densely packed way if you know your way around the language. Are there any questions about the commands we've used here? If you ask me a question about apply, I'll try to struggle through, but I don't understand it well, I must say. Everyone's feeling excited about this. You're ready to start using R today. All right, that's fine. So I want to repeat this, but this time I want to use Ggplot 2. So hopefully you are able to run install packages just fine on your computer and get Ggplot 2 installed. Did that work for most people? No? No? Do you guys have network access? No network access. You do have network access and it didn't work. Oh, that's vexing. Well, I'm not going to be able to correct all of that right now, I'm sorry, but that is one of the pains of using a package in a demonstration like this. So you've seen what it looks like in the base package. We're going to look at it in a totally different system for visualization. So I'm going to start by specifying that I want this library to become usable. I've already installed the package, but now I must inform R that I intend to actually use it. So I grab the library Ggplot2 line. You'll sometimes see that using require instead. They're very slightly different in their effects. As I run library Ggplot2, you can see that I get a warning message. So is it a big deal warning message? Well, it's a package startup warning. And the warning message says it was built under R version 3.4.3. So how fussy am I about this? Am I running a version of R that looks like that? What's my R version? You know, tell you what, I just don't care. If I run into a fault on it, I'll let you know. So for now, I'm using a version of the Ggplot2 library that's designed for a slightly different version of R. I'm not going to cry tears about it. So let us return to our source code. I got tired of typing log2 fold because that's the threshold we use, remember, to say whether something is a difference in effect that's big enough for us to care about. So I created a variable to store the value of a natural logarithm of 2. So I'm going to grab that and throw that in here. So what is that value? Log 2 full. We see it's 0.69. So the natural logarithm of 2 is 0.69. That's very helpful. Now we don't have to type that again. Again, we want to create a vector, but this time our vector is going to be based on whether or not anyone cares about this gene's p-value and fold change. Okay? So let us grab this, and I'm going to go ahead and run it over here, and then we will walk through the command bit by bit. Okay, great, it just ran. So there's some, oh yes, I have a question. Yes, sir.
Our text file cuts off.
Oh, right, okay. Yes, sorry. I will be sending this one around today. I didn't have this written until this morning at 6:30, so sorry. I got to about 4 o'clock yesterday, and I got to the part where I was actually doing the Ggplot 2 thing, and I said, it's going to wait till tomorrow. I'm sorry. So you will receive this full script in email today, along with the URL for this discussion. Sorry, good point. Yes, so this is the Ggplot 2 code that I appended to the bottom of the file this morning. All right, so there were two rules that each gene must pass for us to say we care about this gene. First off, we want a p-value that's what? What do we say about the p-value? A nice high p-value, a nice low p-value? What do we want? What? You want a high p-value? Ah, see, I've already confused things because I've been talking about negative log p-values rather than p-values. Okay, so to say this in two different ways, we want a p-value, an adjusted p-value, that's less than 0.05, which means that we want a nice and high negative log p-value. So a low p-value makes it higher on the volcano plot. Sorry, that's an easy place to get confused. Okay, so we want to see that the adjusted p-value is less than 0.05 if we're going to call this a hit. And we're only going to use adjusted p-values here, only those that have made it through multiple testing correction. The other rule is a little bit complex. We are looking at this on the log fold change scale, which, as you recall, is whether it's to the left or to the right on our volcano plot. And we care about things that are not close to 0. Because if they're close to 0, that means that there's basically a 1-to-1 ratio between red and yellow. Am I repeating myself too much? Okay, I want to make sure everyone's following the discussion. So if we have red and yellow expression levels that are very close together, even if they're found to be statistically significant different, that we have a p-value that claims that they're really different values, we require that they be far enough away from 0 on the log fold change scale that we care about them. So what we're using, I realize that highlighting that might actually make that a little more confusing, so I'm just coming up here. So we're using an absolute value function, We apply that to the logarithm of fold change, and we expect that value to be greater than log of 2-fold. If it's greater than this threshold, it means it's either very far to the left or very far to the right. Those are the boundaries that we care about. So we've added a judgment to our table. It's not a mathematically calculated thing, it's a logically calculated thing. If the p-value is low enough, or a negative log p-value is high enough, and it's far enough to the left or far enough to the right, then we're going to give it a positive evaluation. Okay, so what does that look like? GE threshold. We just computed this thing. I get a whole bunch of falses and a very few trues. So let me run a summary on that instead. Summary GE threshold. There it is. Okay. You remember I was talking about logical or Boolean variables yesterday? Things that have a true value or a false value? In this case, we've created a 1,000 element vector of logical values. And we see that 951 of them are false and 49 of them are true. Okay? Now, what did I tell you about the gold standard answer in this data set? I told you that I modeled this data set so that 1 in 10 of them are truly different. So how many should we find as true differences in these data sets? 100. We had 1,000, 1 in 10 are actually different, and here we see that only 49 of them pass this test of being a big enough fold change and a high enough negative log p-value. So that's already a matter of some concern. There are real differences that have been simulated into this data set that we failed to recover by the statistical method. That's something we have to get used to. Whenever you're doing an experiment in mass numbers of tests, thousands of genes, thousands of proteins, you have to accept some of them will be differential, but you won't be able to recall them. Your sensitivity will be insufficient to get down into that set. So, very worth noting, if you're doing lots and lots of tests, don't expect perfect accuracy on your method for detecting differences. Here we lost about half of them. Okay, with that scary note aside, let's return to our source code. Next up, we're going to create a data frame that stitches all of this information together. As it appears, Ggplot really likes data frames. It really likes sets that have been structured in this way. So what we're going to do is just stick them all together. Remember, gene expression had 11 fields, gene name, 10 intensities. We have our p-values. We have our GE log fold changes. We have our adjusted p-values. And we have this threshold, which is just a yes or no thing. So we're going to create a new data frame that spans all of that information. All right. So when we run it, what happens? We've got our summary GEDF. Oh my gosh, it's got a whole bunch of fields to it. I'm going to pull that over to the side a bit more. Okay. So as we rotate through this, we have gene, we have red 1 through 5, yellow 1 through 5, and then we have a whole bunch of information derived from that. Do we have a quick question?
So I was just checking if you're seeing the relevant flashes, the rest of
Where is the red flash disk?
Flashes 0. That's the exact same as the 5, 6, 4.
Okay. Ah, great. Okay. Yes, right here.
But it's a plugin for
I didn't update this? I thought I did.
I tried it. It's the same.
Oh, that's embarrassing. Okay, well, you'll get it today in email. My bad. I'm sorry about that. All right. So we see that these new values that we've added have been appended onto the backside of this data frame. Yellow 5 used to be the last field. Now we've got the p-values, the log fold changes, the adjusted p-values, and even our GE threshold has all been stapled onto this data frame. So you'll often find little Frankensteins like this get created in the process if you're working with R. If I use the right table function, I could now spit this off to a table that I could then open in Excel and visualize to my heart's content. So that's all feasible for us. So having created that data frame, we can now produce a volcano plot. I want to say that the Ggplot2 library takes a little getting used to. I would say I'm still very early in my learning curve on this one. So why is it called Ggplot? Is it written by Gus Grisham or something? It's not. It's written around an idea that was published, I believe, in the 1990s, called the grammar of graphics. The idea being that there are several features of data visualization that apply across all kinds of different plots. And in this case, we are using several of these. So we start with input data. We have to specify to the function what is the data frame that we're using as our source, GEDF, which was the one we just stitched together. We're using an aesthetic parameter, an AES. The aesthetic is something that specifies what the axes will be like, for example. So on X, we will be showing the log fold changes. That should be familiar from the volcano plot that we did. Our y-axis will be on the negative log of the adjusted p-values. So it's setting up what the ranges look like for this two-dimensional plot. Coloring. Now this is an important idea. In this case, we are communicating to the Grammar of Graphics library the basis for coloring the data points that we're going to put onto this plot. So we're giving it a logical value. Remember, this is trues and falses. We had, I think, 49 trues that we cared about. So it's going to apply a different color whether our judgment was true or false on each one of these. All right. Now, I know it's customary when we're messing around with code to assume that white space doesn't really matter. And I spent probably a half hour this morning before I realized that R cares very strongly whether you have a plus on this end or this end of this line. So I wasted a lot of time there. Just take it for granted that when I pass you the code in email today, you want to run it just as it is. So we're going to keep adding onto this object. So we're creating an object called G that's a Ggplot type. Having set up the aesthetics of the plot, we're now going to specify that it's a scatter plot. And the geometry of point is what they use for defining this. Alongside this, we could do things like specifying the shape of the points. We could specify that they have an alpha value so that you can see if some are overlapping or not. You can set their color. You can set all kinds of nonsense. In this case, I've simply run geom point without any special additions. Down here, we have this theme element, and the theme may not be inherently sensible, but I think we've all heard of legends, right? So we've told it that we want to color the data points differently depending on whether or not they're accepted in our volcano analysis. So we're going to specify that it doesn't show us what the colors mean. We just left that off. If we leave this element out, then it will give us a cue to whether, say, the red dots mean true and the blue dots mean false, and so on. Down here we have the X label. We can label our axes. It's always kind of a nice feature. So we're going to call the X-axis log fold changes, and the Y-axis is going to be labeled negative log p-value. All right, now I'm going to grab that code and actually run it. Copy that. Run over to console. Oh, and I need to have my graphing window reopened. Shoop. All right. Does it work? I'm not seeing it. All right. So I had to actually do more than simply create the G object. I had to tell it to plot the thing. So plot G produces this image. So plot is a base R function, but it knows that G is an object created by Ggplot2. So it says to Ggplot2, the library that's been installed, here, this object is your problem, you visualize it. So plot hands off G to Ggplot2, and out pops our beautiful image. Now isn't that nice? Now I think it's a lot clearer which data points here we're going to care about. Things like this, even though they have a significant p-value, are too close to no change in fold for them to be visualized, for them to be considered accepted in this. But once again, we've run into this problem that figuring out where we are on this plot, where's the boundary between significant and insignificant p-values falls. So we're going to add some new elements to this using the grammar of graphics language for that purpose. And in this case, those lines are right down here. So we're going to add to the G object. We're going to add a horizontal line with an intercept at the negative log of 0.05. It's the same as what we did before, except instead of using the AB line thing, we're using the H line grammar statement. We're also going to add two vertical lines. One that has an x-intercept at the log of 2-fold, and one that has an x-intercept at the log of 1/2. Remember that we have to have these, we have to take into account that yellow may be greater than red as well. So if I run that command, we finally get our image. Great, okay. So, having started with base graphics, we got a competent image, one that you could very comfortably publish in a journal. But here we have something that's pretty, that uses color, and that gives us a little more ability to extend upon this image. What if, for example, we wanted to be able to differentiate this area down here where we have a whole bunch of overlapping symbols. That's kind of a mess, right? We know that there are how many blue dots on this page? 49, right. We had 49 recovered differences, which means that there are 950 of these red dots. You might think to yourself, well, goodness, they must be overlapping because that just looks like a big red smear down there. So one of the things that we could do is change the alpha or the gamma value of these points so that if you have a whole bunch of them, you get a nice dark color, but if you have just one, it has a relatively translucent effect. You can do stuff like that with the grammar of graphics. If you try to do that with base graphics, on the other hand, you're going to get yourself into a rather lot of programming trouble. So Ggplot makes it a lot easier to produce presentation-ready graphics. You can argue, of course, that if you had the base graphics, the black and white one that we generated a few moments ago, there are very few journals that are going to turn their noses up at such a thing. But color really can help to capture your audience, and Ggplot handles it rather nicely. This is not to say that in base graphics we are prevented from specifying that the dots should be red or the dots should be blue. One of the simpler things to do would be to subset the dots and grab out those that had that passed and specify that those be plotted differently than those that didn't pass. And then you could use colors for each of those and get the same differentiation effect. But in general, if you're going to do a whole lot of customization to your graphics, Ggplot 2 is your best friend. Okay, now I've been running now for about an hour and a half. My voice is starting to get a little weak on me, but I think it would be a good moment to pause for questions. So I'm going to pause right here, and after that we're going to talk about how we simulated the data that we're presenting here, because that part of the story is an important one as well. No questions? Okay, so, yes, sir.
Okay, is this to understand, let's say you want to put out, do you just go about thinking, like, how do I know what to read, or how do I get to that?
Yeah, well, honestly, there hasn't been a whole lot of thinking about visualization of data that has permeated into the scientific community. There are some people in the world who have done some really amazing scientific visualizations. I'm trying to remember the name. The Art of Scientific Visualization, is it? By Edward Tufte. People like that have gone through history to look for really key examples where a visualization made a difference. There's a very famous plot of Napoleon's armies as they approached Moscow and retreated from Moscow. And you can see how large his army was, what cities they were marching between, what the date was, what the temperature was, all of that in one image. And examples like that are, they're kind of humbling, really. These days in science, we tend to say, well, if I'm doing a differential expression analysis, I must do a volcano plot. And a lot of that is learned rather informally. But consider the problems of the old microarray bicluster plots. These are the ones that have that appear in black, and they have a bunch of red and green spaces on them to represent whether a gene was up or down. These biplots are really common in the gene expression literature. But think about how big the fraction of the population is that cannot distinguish red from green, right? That's a terrible color combination to use for showing these differences. So I would say that we need more people thinking actively about why I'm choosing this palette rather than another. If I were to print this in black and white on my departmental printer, would I be able to tell these dots from those? So a lot of the coloring strategies that we use, a lot of the visualization strategies can use a lot of thought concerning the context in which they will be used. In this case, we didn't even tell the software, we want these to be red and these to be blue. We told it that these are trues and these are false. You figure out what they should be colored, which is a little strange. So this is a default palette, we would call it. This is the set of colors that it uses when given a two-way classification of points. Might that change in a later version of Ggplot too? Sure. Maybe the next version of this software will make these purple and these red. I don't know. But the structures that we use for visualizing these data are always worth thinking about. In this case, we note that there's no grid, really, to be seen, especially in the base graphics. But if you look at it carefully, you see that this is a light gray square bounded by a white grid box. So it's already giving us a little bit of indication where the units fall on the vertical axis and on the horizontal axis. So these are nice features, and there's so many people working in the space of scientific visualization on the Ggplot 2 project that using it probably means that you're going to gain from their insights on what makes a good graph and what makes a bad graph. Does that answer the question? Okay, so let this be your reminder then that when you produce posters or slides to be presented at an international conference, don't depend on your viewers being able to tell red and green apart. All right, minor point there. Okay, now I'm going to walk through the data that we used to, the data that we created for this exercise. I spent most of my time yesterday just getting that part working correctly, not so much the visualization code. But I want to walk you through that because there are a couple features here that really matter quite a lot. I'm going to try to make the text a little larger. I can do that in Emacs, I think. So I'm going to set my default font to Consolus, and I'm going to boost that up to 20 point font. Boom, look at that. Can everyone read that? All right, good. All right, so we're going to start with this first bit, random string. Random string. When I left class yesterday, I did not know how to get a random gene label created. And so I ended up doing what programmers around the world have done since the invention of the web, essentially, which is to go Google for an answer. And unsurprisingly, I found my answer on a site called Stack Overflow, which is a place where a lot of programmers hide out to discuss the best way to do X, Y, or Z. Sorry. So we see in this case that we have a random string function. You see, we can define our very own functions in R if there's a kind of math that you do very frequently. If, for example, you're computing Euclidean distances all the time, you might define a function for that purpose. If you're trying to compute how many different handshakes you can have if you've got 10 people at a cocktail party, you might define that as a function. It's actually quite easy to do. That's fine. So in this case, the software is generating a sample from the collection of letters. So I've mentioned before the possibility of sampling numbers from the uniform distribution or from the normal distribution. In this case, we're sampling from a set of letters, a set of X samples. So if I tell it that I want to generate an 8-letter name, I pass it X equals 8, and the software knows to use that to sample out 8 letters. Replacement equals true means that just because I've used an A already in this label, it doesn't bother me to use it again. So replacement equals true is set there. And then I use the paste function to glom all of these things together. Glom is a very technical term. It means to stick them together. Right? So we started with a vector, 8 items long, each one being a letter. The paste function crammed those together so that they were one label, one string that had 8 letters in it. And then it returns, at the end of the function, the set of 8 letters, or the set of X letters that it has generated. So that function, I'm going to call 1,000 times. So by writing it like this, I can use it in all kinds of different places in my code. So that's a very compact way to do our gene name generation. You can see that I set out my comments. Comments in source code are very, very valuable because they remind you what you were thinking when you created that line of code. If you come back to your R script 6 months later, you would like to be able to figure out what you were thinking. And so having some of these lines of comments in here really do matter. And in R, most frequently you see comments that start with the a hashtag. So hashtag, simulate gene expression data for 1,000 genes in 5 replicates. That was what I chose to do. But you see, I've set it up so that I can modify this code really easily to make 10,000 genes or 70,000 transcripts, for example. So here we've set the number of genes to be simulated to 1,000. I've specified that the number of replicates in each cohort, just using 2 cohorts, will be 5. So next, I needed to make some decisions about what fraction of all of the genes were going to be truly differential. And I decided that I was going to use a 1 in 10 rule for this purpose. And I'll show you how that's implemented just below. One of the most common things that we do when we're starting some complex code is to knock out a bunch of dummies for us to fill up later. So we had 11 columns in the tables that I provided you. The first one is just one vector of characters. Those are the gene names. And you can see that I've repeated, that's what the REP function does, I've repeated the NA value 1,000 times. Remember, num gene is 1,000. So what is NA? Does anyone recognize that? NA in statistical lore basically means not applicable. It means this value has not been set yet, or it's a missing data point, something like that. So here I've taken the NA value and written it 1,000 times into a vector called gene names. So I'm not just going to start by writing those. I'm going to start by creating an empty vector for them to go into. Similarly, I've defined reds and yellows as matrices. We talked about those yesterday. I wanted to have 5 columns of them, and I wanted to have 1,000 rows in it. So we've got these 5,000 numbers all nicely formatted, but again, it's filled with NA values. You might ask, why didn't you specify you wanted 5,000 NA values stuck into this? And the reason is I didn't have to, because I already told the R that the matrix will be 5 columns wide and 1,000 columns tall. So it's simply going to repeat NA until it has all of them filled. That's one of the rules for doing these inserts. And I do exactly the same for yellows. Now, I mentioned that I'm a big fan of for loops, and here's where I've used them in this case. I'm going to scroll down a little bit. I have a really tall loop here. Oh. I'm going to try, I'll just pull it to there. Okay. So this is the top of the loop. So what does this for loop do? What's the first value that I is going to take on in this loop? I heard it. Say it loud. The first value is 1. Thank you. Right. So it's going to take on all values from 1 to 1,000, because that's what the number of genes is. And each value within that series, it's going to perform the following steps. And there are a lot of them. So I'm going to show you down at the bottom where we hit the bottom of this loop. But for now, I want you to be thinking, we're no longer concerned with the whole table here. Our focus is on one particular row in that gene table that we need to analyze. So we're starting by populating the gene name part. So I'm not telling it how to set the values of all elements inside the gene names vector. I only care about this ith value. You'll frequently see computer science terms like that. So in this case, I've told it I want random strings of characters up to, just 5 letters long. I could have set it to 8, I could have set it to 4, and so on. What I found is that if I set it too low, I ended up getting the same gene names on different rows. I didn't want that. So I set it to 5. That worked okay. Next, I'm using a family of functions here that all start with R. So there's runif, there's rnorm, there's rexp, and there's rpois. There's a whole bunch of these. All of them are designed for creating random samples from known distributions. So exp is what kind of distribution? I think I heard it. Exponential. Very nice. Okay, so the exponential distribution is not a bell curve. It's kind of lopsided. In fact, we can visualize that very quickly. I'll just pop over here to my R console, and I'm going to say plot the density, density, not destiny, Rx 1,000. I'll do 10,000 points because I'm just feeling expansive. Okay, that is an exponential distribution. So in effect, what I was telling it is that typically, I want the intensities of genes to be nice and low, but on occasion, I want them to be very, very high. You see that? So this is what the distribution of those mean values will look like. Very lopsided towards low values, but occasionally producing some very high ones. Sorry, I did that in R rather than RStudio, but it was easier. Okay. So I'm having it randomly select what the value of that gene intensity will be. And now I've got some really wild math going on here. So remember, an if-then statement allows for us to do two different possibilities on the basis of a logical test. I've given myself 20 more minutes on this, and then I'm going to stop because I don't want to go over time at all. So I'm going to use I % same to difference ratio. Isn't that squirrely? What on earth does that mean? Right, so I want you to hearken back to your grade school days where we would divide numbers by other numbers. So imagine that you divided 15 by 3. You got two parts to your answer. 15 divided by 3. You're going to say the answer is 5, thank you. But the other part that's going to come out of that is that you had a remainder of 0. I know that sounds pedantic, but if I tell you to divide 16 by 3, you're going to say it's 5 with 1 left over in remainder, or you're going to say it's 16/3 if you're being really pedantic. But you're going to be good to me, and instead we'll think of it as a remainder. So this is called a modulo operator, a modulo operator. Instead of saying I divided by same to different ratio, I'm saying I modulo difference ratio, which means it's going to give us the remainder as the output from that. Now, I didn't say equals 1 or equals 0 or equals whatever, and this is a bit of computer shorthand, I must say. In this case, I've simply taken the value of that modulo straight out, and under R's basic set of default understandings, the value 0 is handled as false. The value of anything above 0 is treated as true. It's weird but true. And you'll see this showing up a lot of times in computer science too. So in this case, the only case in which this returns a false value is what? To return a false value means I have a remainder of 0. And that only happens when what relationship exists between I and same to difference ratio? What's the first time that you get a remainder of 0 as we start from 1 and move upwards? Okay, well, we can just walk through it. When we have the value 1 and we divide that by 10, we get a remainder of 1. If we have 2 divided by 10, you get a remainder of 2. You run 3, remainder versus 10 is 3. This keeps going until you hit 10. As soon as you get to I equals 10, and divide by 10, you get a remainder of 0. So that's the first time you get a false. In effect, every time this software has a value of I that is evenly divisible by 10, it's going to make it a differential gene. So that's the sneaky business. So if it does have a remainder, then the log fold change is 0, which is to say that red and yellow will be balanced in intensity. Otherwise, this log fold change is, well, now what's that? Our norm of 1. Our norm of 1. Well, we plotted the other just a moment ago, so let's clear that away and pop over here. I'm going to say plot density R norm 10,000. That is a normal distribution. So the software was deciding how different these fold changes would be by drawing it from this distribution. And it's doing it on a log fold change as well. So it might accidentally, get a value that's very extremely towards yellow, or it might get a value that's extremely towards red. But most of those fold changes are going to be quite small fold changes. The short version for this is in the volcano plot. I wanted to make sure I had some values that were significant, but not major shifts in either direction. Okay, we have to change that back to a linear fold change because that's a log value, and I had to use the exp function for this. Exp is a pretty easy little function to understand. So I can say exp of 1 is 2.718. Does anyone remember what 2.718 is? If you're thinking about logarithms, this is a very special number to you. E, thank you, that's lovely. Yes, so, oh my goodness, how is that so small on screen? I'm sorry. Well, 2.718. Okay, so the exponential function puts you back in linear domain from a natural logarithm number. So if you feel comfortable using the log function in math, think of exp as its opposite for undoing a natural log. All right. So I'm going to transform the log fold change into a linear fold change. Now there's some math here. And if you really like math, I'm happy to walk you through it. But the short version is that I knew I had a relationship I wanted to have between A and B, some linear relationship, a ratio between the two, and I knew their mean value. But how do you find what value A and B should be if you know only their mean and their ratio to each other? Well, if you remember your math classes well, you will know that that means you have two equations with two unknowns. You can solve for A in A plus B divided by 2 equals mean. And you can solve for A in A over B equals fold change. So you solve both of those for A, set them equal to each other, then you can solve for B. So that's what I did. This B mean equals 2 times the mean divided by 1 plus this linear fold change, and out pops my B value. Then I can compute A simply by applying the fold change backwards. Okay, now we have a mean value for A, we have a mean value for B. Next we need to figure out what data we're actually going to tell the user instead. So for this, I'm going to grab 5 values from the normal distribution that are centered on the mean value for A and that have a set standard deviation. I had to figure out how noisy the data should be, and I chose to make them 1/10 the noise of the mean, which means that if you have a very intense signal, you have high noise associated with it. It's 1/10 whatever the mean value is. If you have a very non-intense signal, you have relatively little noise around it. So this was a critical decision because if this mean, if this standard deviation is set to, say, half the mean or the square root of the mean, you end up with a lot of differences being completely undetectable. And I want this to reinforce something I told you earlier in the hour, or in the 2 hours, which is to say that if you're trying to detect a difference between two numbers, the amount of variation around those means has everything to do with whether you can find it or not. So I needed to control the standard deviation to a level that would still allow us to find those differences apart. Generally speaking, when we use models for interpreting microarray data, we frequently assume that the standard deviation is the square root of the mean value. And if I did that, you would find that a lot of these differences were just too noisy for you to dig out. All right, from there, I was able to write into the reds array the intensities we simulated for it. I was able to write into the yellows matrix, sorry, not array, the set of values for the yellows. And then I had a little bit of code in here. Cat is a useful function to know about when you're writing in R, and that's because cat will spit out to the screen values that you want to know. Anytime you're debugging code, it's very, very valuable to you to be able to look at what is the current value of X. And this is where I did that with the cat function. So you can see I told it to spit out the gene name, the current gene name, use a tab character, that's what this \t means, the mean value, another tab character, and then at the very end, I threw on this \n. \n means go to the start of the next line. So I had 2 special characters in there, \t, \n, those are tabs and start of new lines. Both of those are very valuable to use in conjunction with cat. Okay, at the end of the day, having finished all 1,000 of these loops through the through the gene names. I build a data frame from it using gene names, reds and yellows. I supply some columns, some column headers for the data frame that I've created. And then I use write table to dump it off to a file on disk. And you, in turn, have received that data file in your email. So it was a bit of an adventure just to find a way to make these data such that you would have known differences in there. And if you're curious, I would encourage you to look back into the code that we did this morning to ask what happened to them. Right? We know that there were 100 values in this table that really did have that did have real differences between their means. So where did they go? We claimed that 45? 49? How many of them? 49. We found 49 differences between red and yellow. Were all of them even multiples of 10? I don't honestly know. Many of them were. But you get to this point where trying to recover one more significant p-value out of that roster ends up digging you into entries that aren't really different. So I hope this has been useful to you and that you've learned a lot about how R can help you out do some more complex kinds of data analysis. And I want to point out that if R is not your cup of tea, if you find R just too daunting to work with, there are tools like GraphPad Prism, which can do things like this as well. So I hope that at the very least you feel a little better armed to understanding the kind of code bases that we typically use in biomedical research. Now, I don't see you all again until next Monday. I am trying now to find out where we're meeting in the morning on Monday. If it's this room, I will probably run this key over to Brights and make myself a copy. But I'm intent on seeing that we have a place to sit and that we have a working projector in whatever room we're meeting at 9 o'clock on Monday for the practical sessions associated with bioinformatics. We'll be doing the lectures in the afternoon, I believe in our division's seminar room between 2 and 4. More frequently, those run to an hour and a half rather than 2 hours. I get really sleepy in the afternoon too, so I'm hopeful that we can keep that all nice and dense. But for now, it's been really nice to work with you. This video will appear on YouTube this afternoon, and hopefully you'll find it useful. So thank you very much. See you next Monday.